Hello and welcome. The subject matter of this video is multidimensional arrays. So let's consider the declarations on this slide. The first one is double A 100. This declaration declares a one-dimensional array of type double and of length 100. This is the kind of arrays that we have seen so far in this course. This is a single dimensional or a one-dimensional array. The next declaration is int b, then 4 within square brackets followed by 6 within square brackets. This is a two-dimensional array. So a single dimensional array has a length that needs to be specified during its declaration. A two-dimensional array has, two dimensions. You can think of the two dimensions as length and width, if you like. So this declaration declares a two-dimensional integer array of length 4 and width 6. The third declaration is that of a three-dimensional array. It has 3 dimensions, and you need to specify each of these dimensions during the declaration. This declaration char c followed by 3 numbers, each enclosed in square brackets. This declares a three-dimensional array of length 5, width 4 and height 9, if you like. And similarly, for a k-dimensional array has a size for each dimension. Let Si be the size of the ith dimension. If array elements are of type t and v is equal to size of t, the array declaration will allocate space for s1 times s2 times all the way up to sk elements, the product of these si's, which is the product of si's times v bytes. For instance, this declaration, the first declaration, allocates 100 times size of double, which is, let's say, 8 bytes in my computer. These many bytes. This declaration, B46, allocates 6 times 4 times size of int, which is, let's say, 4 bytes. That is 24 times 4, 96 bytes. And this declaration allocates 9 times 4 times 5, that is 180. And each character is 1 byte, so 180 bytes. So let's focus on two-dimensional arrays. So that's the simplest to understand, and that will lead to the concepts of general multidimensional arrays. So as we saw, it has two dimensions. So consider this declaration A35. It declares an array that is capable of holding 15 integers, and you can think of those 15 integers as arranged in a matrix with, let me just correct it here. A45. So this diagram is that of a two-dimensional array with 4, length 4 and width 5. We'll think of it as a matrix with dimension 4 cross 5. So a matrix with 4 rows and 5 columns. And this is how it's the numbers in this two-dimensional array are arranged. You can think of the first row, or let's say row 0, because indices start from 0 in C, as we saw. So let's say the rows are 0 through 3 and the columns are 0 through 4. Okay. So the first row corresponds to the first index being 0 and the second index taking all possible values. So here the first index is fixed to 0 and the second index cycles through its entire range, that is 0 to 4. Similarly, the first row corresponds to the first index being 1, row 1 corresponds to the first index being 1 and the second index going through all its values, all possible values. Similarly, the columns can be thought of as the second index being fixed while the first index cycles through all possible values. So here, for instance, column 2, but the second index is fixed to 2 and the first index takes all possible values, that is 0 through 3. Okay. Well, let's progress. So there are numerous ways to access elements of a 2D array. Yeah. So Aij is equal to all these expressions. So let's try and understand each of these. So let's say Aij is a 2D array. So this is what it will look like. So this is A00 and this is A m minus 1 0. So let's say this is A m n. So m rows and n columns. So the first index goes from 0 to m minus 1. The second index goes from 0 to n minus 1 and so on. So this one is A m minus 1 0. I'm sorry, this should be n. And up to this is A m minus 1 n minus 1. Okay. So for one dimensional arrays, we said that the array name stands for the address of the first element of the array, the base address of the array. So in two-dimensional array, AI, for instance, stands for the base address of the ith row of the array. So A0 is a pointer that points to the first element of row 0. A1 is a pointer that points to the first element of row 1 and so on. So then AI plus J, what is that? This addition is pointer arithmetic. So we are adding an integer to a pointer and we know what it means. So A0 is this. A0 plus 1 points to the next integer, that is A0 plus 1 points here, which is A0 1 and so on. And in general, A0 plus J points to A0J, and more generally AI plus J points to AIJ. This is a pointer that points to AIJ. So if you put a star operator, apply a star operator on this, what you get is AIJ. So AIJ is equivalent to this expression, star AI plus J. Okay. Now let's understand the later expressions. Now A. So what does the array name A stand for? For a two-dimensional array. So for a one-dimensional integer array, let's say the name of the array stands for a pointer, as an integer pointer that points to the first element of that array. Now for a two-dimensional array, we will think of a two-dimensional array as a one-dimensional array of one-dimensional arrays. You see? We can think of this two-dimensional array as this one dimensional array, and each of them is itself a one dimensional array. Yeah, and so each of them is a one dimensional array. So this array A is really an array of arrays. Okay. And now how does the pointer arithmetic work? What does A plus I mean now? It's again you're adding I to a pointer, but what is the type of the pointer? So the pointer points to an array of one dimensional arrays, or equivalently an array of pointers, each of them pointing to an one dimensional array of size n. Yes. So if I add I to A, what I get is the pointer that is pointing to the ith row of this array, or equivalently A box I. Yeah. So A plus I is equivalent to AI, yeah, which is a pointer that points to the ith row of the array. A plus I points to the ith row of this two-dimensional array. And so what is the type of this pointer? It's an array pointer. It points to an array. So what is star of A plus I? Well, it must be an array. Because, if x is an integer pointer, then star x is an integer. So if A plus I is an array pointer, then star A plus I is an array. Yeah. But what is an array? Well, an array is equivalent to the address of its first element. So star A plus I is the address of the first element of the ith row of the array. And then, you can put j after it, and then the usual array indexing works, and this is equivalent to aij, which is the jth row of the array ai, one dimensional array ai. Similarly, star A plus I, yeah, bracket j, is the same as adding j to star A plus I and then dereferencing it. This is pretty much the same. Why? If B is a single dimensional array, then B of j is equivalent to star of B plus j. Yeah. Now just replace B by here you just replace B by star A plus j, A plus I here. The star A plus I is now the single dimensional array that is the ith row of this 2D array. This one is straightforward, and this has got to do with the way 2D arrays are stored in memory. Yeah. So we have a more detailed slide later about the way they are stored in memory. So let's do that first and then come back to it. Sorry. Okay. So this slide contains the information that we covered just now. This should be small I. We can think of AI as the ith row of A, and we can think of aij as the element in the ith row jth column. The array name A is a pointer to an array of 5 integers. The base address of the array is $A00 that we know, and starting at the base address, the compiler allocates contiguous space for 15 integers. Yeah. Okay. This is the storage mapping function. The mapping between pointer values and array indices. Int amn, the storage mapping function is as follows. Aij is equivalent to, this is the address of Aij. You start from the base address of the array, the address of the element in the index 0, 0, plus n times I, so n is the second dimension of the array, plus j. And why is this true? Well, what does it mean intuitively? So let's come back to this picture again. Yeah. So this is how the array elements are stored. So the first row is stored in contiguous memory locations, then the second row, then the third row, then the fourth row, and so on. So what is the location? What is the address of, let's say, ampersand A04? What is this? Well, this is just ampersand A00, plus 4. Right? Just pointer arithmetic. Now, what is ampersand A14? Well, this is, ampersand A00. Yeah. Then you have to add the number of elements in the first row, which is 5. Yeah. One times 5, and this one has got, sorry, this is not I, this 1 times 5, and this one is the same one as appears here in the first index of this, and then plus 4. So in general, ampersand Aij, is, the base address plus the number of elements in I rows, which is I times, so in general it could be amn, yes, I times n, because the length of each row is n, is equal to the number of columns, plus j. Yes? Okay. Which is what is written here. I'd like to point something out to you, which is going to be important later. In this expression, the second dimension appears, but the first dimension does not. So n appears, but m does not appear. So to evaluate the address of Aij, I need to know capital N, but I do not need to know capital N. Yeah. Let's keep this in mind. It will be relevant soon. Okay, how are three-dimensional arrays stored in memory? Similarly, well, first all the elements with the first index being 0 are stored. And then how are they stored? Well, if I set the first index to 0, what I get is a two-dimensional array, and they are stored exactly as we saw. Then for x equal to 1, the resultant two-dimensional array is stored as we saw, and so on. So you can extend the argument that we did for 2D array and derive this storage mapping function. So ampersand A000 is the base address of this 3D array times I times yz, because yz is the size of the 2D array obtained by fixing the first index, plus then this is the standard storage mapping function of 2D arrays that we saw, z times j plus k. And in the header of the function definition, the following three parameter declarations are equivalent. So before coming here, let's note here that in this expression, x does not appear. Y and z appear. Yeah? Only y and z appear. So while uh, while writing functions, while defining functions, if one of the arguments is an array, we need to specify the second and the third dimension of the array if it's a 3D array. But we can leave out the first. We can put it as well, but that's optional. We can either put a, then an empty square bracket, or star a. Yeah. But we have to inform the function the second and the third dimensions. Yeah. And this is because otherwise the function will not be able to compute the storage mapping function. And the first dimension is not useful for computing storage mapping function, but all the other dimensions are useful. In general, for m-dimensional arrays, all the other from second through the mth dimension, they are all useful. And while passing arrays to functions, all these dimensions need to be passed. When a multidimensional array is a formal parameter in a function definition, all sizes except the first must be specified so that the compiler can determine the correct storage mapping function. This is exactly what we said. So in the header of the function definition, so here is the definition of a function which takes in a two-dimensional integer array, and as you can see here, the size of the second dimension is specified and the first one is not specified, but there is an empty bracket here. And you could use any three of these parameter declarations. They are all equivalent. You can initialize multi-D arrays like this. You can just list 6 integers. Int a 2 3 is equal to this, and yeah, you do not have to tell the compiler that 1 2 3 is the first row, 4 5 6 is the second row, because that's the only possibility. If you mention the sizes, the compiler knows the sizes, and that's the only possibility, that 1 2 3 is the first row, 4 5 6 is the second row. Or you could make it more explicit in your definition. Yeah. Or you could skip the first size and specify the second and write it like this. And from this initialization, the right hand side of this assignment, it's pretty clear that you know the first size is 2. This is a use of type def. We have seen type def many times. So type def double scalar. So scalar then becomes you declare the type scalar as to be the same as, you define the type scalar to be the same as the basic type double, and then you can write type def scalar vector within bracket capital N. So then vector becomes synonymous to an array of size n, a single dimensional array of size n of type scalar, that is type double. Then you can define a matrix to be a two-dimensional array of type scalar and the sizes being capital N and capital N. Or equivalently, you can define you can define matrix to be a one-dimensional array of type vector of size n, and vector is itself a one-dimensional array of type scalar of size n. You could use any one of these two definitions of matrix. So here is a function that takes in 3 vectors. So what are vectors again? Vectors are 1D array of type scalar. Yeah. So each of these 3 variables x, y and z is a vector. Yeah. And then this function vectorially adds x and y, and vectorially adds y and z and assigns the result to x. That is, it just adds y and z component wise and then assigns the result to x. So each of these additions is an addition of type scalar, which is the same as double. So each of these is a double addition. this function takes in two vectors x and y and returns its dot product. X and y are double vectors, single dimension. So the dot product is of type scalar, same as the type double. So this is done in the straightforward way. There is a running double scalar sum which is initialized to 0, and then you go over each index from 0 to n minus 1, and then add the product of xi and yi in your running sum. Finally, you return the sum. Okay. So here you take in three variables of type matrix. So matrix is a 2D array of type scalar or a 1D array of type vector, as we saw. So in this function, we think of it as a 2D array of type scalar or equivalently type double. So you multiply x and y, treating them as matrices, and then store the result in Z. So how do you multiply matrices? Well, how do you compute the ijth element of the matrix Z? So I goes from 0 through n minus 1 and j goes from 0 through n minus 1. So the ijth element is the product of the ith row of the matrix X and the jth column of the matrix Y. And this is what this loop does. It initializes xi j to 0, and then this for loop multiplies the ith row of the matrix X and the jth column of the matrix Y, and that sum and that product gets assigned to xij over this loop. So this product of ith row of matrix X and jth column of matrix Y is, the first element of X, the first element of the ith row of X times the first element of the jth column of Y plus the second element of the ith row of X times the second element of the jth column of Y, and so on. So you compute this sum using this loop and assign it to xij. And these two outer loops, make sure that this is done for every ij. So this program has the effect of filling the entire matrix Z with the correct entries, which is, so after its execution, Z is exactly equal to the matrix product of X and Y. Thank you.